analogy, right? R is like a phone that you have recently bought, and the libraries that you download are like the apps that allow you to do things. And the tidyverse is one of those libraries, and it's very widely used in science. It's widely used in the quote unquote data science world. So that's what we will talk about today. All right, first a little motivation. So a couple of years ago, I got this real email from a friend, and she asked, when should one use IES versus not use it? I have a reviewer asking me to do it. My answer was, well, just put it online, and if you want to put it in the main paper, great. If not, just leave it as an online appendix. And then my friend replied, the reason it is an issue is because these are really old data, and I'm struggling with a mess that's irrelevant. Graduate students back up and find the original raw data to calculate percent errors. I think I cannot see my full screen. Percent errors, extract RTs. Poor data management is the reason I'm unproductive, and it never seems to get better. FML. I think a lot of us can relate to this last section. I certainly did, and I had a couple of embarrassing moments in which I simply don't know how I got to a place in my analysis, and I cannot reproduce it. So, uh, I think spending some time and effort in learning these tools is quite important. Okay, so as I said, my friend has a lot of company. Everybody knows about the file per problem. But we also have a little bit of a dirty underwear drawer problem. We have very idiosyncratic data stewardship, and this data stewardship systems, if we can even call them a systems, are not often something we're proud of. So this is a really cute quote by Hadley Wickham, which is probably one of the most important statisticians alive. And he's the creator of a lot of these tools. Like families, tidy data sets are all alike, but every messy data set is messy in its own way. All right, so the place where we're going to try to get to is a form of data that we are all very familiar with. And I would say that psycholinguistics was one of the early adopters within psychology of this format of data. And essentially, the idea is that each variable is a column, each observation is a row, and each type of observational unit forms a table. Usually in our, for example, response times experiments, each variable, meaning, what trial number we're talking about, what's the stimulus, what is accuracy, what is the RT for that trial. Those would be the columns, and each trial is a row. Now, untidy data, and here when I use the word untidy in this context, I don't mean it as a value judgment. It's just as a contrast to the tidy format espoused by these tools. So in untidy data, sometimes we have column headers that are value, not variable names. Multiple variables are stored in one column. Variables are stored in both rows and columns. Multiple types of observational units are stored in the same table. And sometimes a single observational unit stored in multiple tables. This is the format of Excel, I would say, where Excel is so it's such a blank slate that we can do all kinds of things in it, right? Like use one column in which we put averages, and right below it we use it for something else, and so on. So the place that the tidy data is where we want to arrive, and the process to get to that tidy data should be reproducible, and essentially, what I refer to as reproducible in this context is computational reproducibility, and that means that if we start with the raw data, we end with the same results every time. okay? There are some threats to computational reproducibility. The biggest one I would say is copy and pasting. Uh, for the obvious reason that that requires a motor process by a human being, and that is not computational. And I mean, computational, all right, you get it. It's not computational in a programmatic way. Manual entries, overwriting files, and overwriting columns. Those are four threats to computational reproducibility. And they are threats to computational reproducibility because, for example, if I overwrite a file, if I open a data file and I do something with it and then save it after doing that something, even if it was correct, I cannot reproduce from the raw data to the new version because I have already lost that file. Overwriting columns would be another example. So the solutions for this are to code the data wrangling, never copy and paste, document everything, and arrive to tidy data. And that's what we will do today. All right, so I think I'm gonna leave it at this in this little conversation. So now I'm gonna move on to the RStudio to show you how it's actually done. All right, so this is RStudio Cloud, and you know this is the kind of situation in which this online thing makes it difficult because I cannot have a show of hands of how many of you have used RStudio before, but I'm going to assume that you know at least a little bit about it. That you know that you have to write your code, and you know that there are objects that you can assign values to, and you know that you can download data, or you know get that data files from your local directory and stuff like that. So that's the only assumption that I will make. I will tell you a little bit about what is this environment, the RStudio environment, what is an RMD file, and then I will show you some of the functions of the tidyverse. Okay, so the environment in RStudio is divided in different windows. And you know, you can organize your windows in different ways, but this is the default way in which, you know, if you just simply open RStudio, you will see your windows organized. On the left top side, on this side, if you open a file, or if you create a new file with code, you will see a relatively blank screen on this side. In this case, I'm gonna close it. I'm gonna close it. So if you open RStudio from scratch, you would see something like this. But in this case, I opened this file that I put already in my environment. I'll tell you in a second what this window is all about, the bottom left. Okay, so in this window, we can see just text in addition to code, and I'll get to that in a second. So if we use kind of like a recipe book format or a recipe book analogy, whatever we put on this side, on the top left, is our recipe, our ingredients, and some commentary about our recipe. On the bottom left, we have the console and then other stuff. I'm not going to talk about the other stuff today, but the console is the engine that carries out the computations. So I don't know if you, for some reason, have a question of what is 200 divided by 10, you can put it in the console. And if you want to create a variable with a silly name like X, you can now have a variable called X. On the top right, you see the global environment and a bunch of other things that also I'm not going to get to. in the global environment, you see the objects that you have already created. So for example, I created X, so now it appears here. And I created other stuff for the challenge that I was telling you about before. It's here, but we'll get to that later. The bottom right has a bunch of different options that we will be using. The first one is the files. So if you have a project open in any particular file, in any particular directory in your computer, you would see the files in that directory in this window. Because we're doing it from the cloud and I created the project, the files that are available are the ones that I set up. Uh, um, so these are just regular files. This is the data file that we will use today. This is some background information that I had of my subjects that I will use as well. This is the file that we have here, and I'm going to open this one too. And this is the challenge that I was going to propose to you for the end. Okay. In addition, if we create a plot, we will see it here in this tab. And if we need help, we can go to this other help tab, obviously. Okay, I'm gonna go back to my files. All right, so that's the R environment. Now, next up, RMD files. RMD files to me are a life changer. I have made a habit to always have an online appendix in which I have my entire R session in an RMD file that then I can turn into a PDF. I'll show you how to create the PDF in a second. But essentially what an RMD file is, it is a self-contained session in R. So that is great because it ensures computational reproducibility. Anytime that I create either a PDF file or an HTML file or a Word file based on this document, I'm always going to get the same answers, assuming that my raw data files have not changed. Okay, so you know, when you submit a paper for publication, right, you can always put your whole session in one of the repositories and people will see exactly what you did, what were some of the data quality and quality assurance steps that you took to make sure that you had the right number of trials or whatever the appropriate measures could be. And also it includes every analysis that you carried out. Anyways, so let me, that's a function of this RMD files. So let me tell you now the two main components of an RMD file. Essentially, they are text, which are kind of the white section, and R chunks. R chunks is where we put the R code. And they are separated by this kind of like a back, well, if you're a Spanish speaker, accent in the wrong way, but if you're a French speaker, I guess accent in the right way, accent mark, and then a squiggly bracket, the letter R, and then you close the chunk with other squiggly brackets. I'm sorry, not with squiggly, with accent marks, and that's it. So you can probably notice here that there is a difference in the background, right? So the gray background implies that our code is coming up. The white background just implies that it's regular text. So in the regular text, I can write anything I want, right? I can say, or whatever. It's just text, nothing more, nothing less. But it's great because it fulfills one of the goals that we have to tidify our data process, right? Which is to comment and document everything. We can document everything here. Okay. It follows the Markdown format. So I'm not going to talk about Markdown at all, but it's a simple way to give your documents a nice look. All right. So, but let's get to the code part. All right. So let me tell you a little bit of what this data is all about. I'm gonna open my raw data, subject 0 CSV. You know what? This might be a good chance for people to ask questions. So I'm going to stop the sharing so that I can see if there are questions. Questions so far?
So if anybody has a question so far, you can feel free to unmute yourself and go ahead and pose that question. Alternatively, you could enter it into the chat. Dr. Gomez, I'm not sure if you can see the chat at the bottom, but one question did just come up. It's how did you make the RMD file?
Oh, yeah, I'll show you in a second, but good question. All right, great. So I'm going to go back to sharing my screen if there are no other questions, and then I'll answer that question with my screen shared. Okay, so the question was how did I create this file? It's very simple. You say file, oops, new file. There are many different versions of this format of having a file where you put your code. Our notebook is very similar to our Markdown. Our script only has our no text and doesn't create the nice PDF or Word document reports. So I have a preference for our Markdown. And our Markdown in turn has its own options. And for this, I created a document but for example, my presentation earlier today was created with the presentation option, and I created PDFs. But you can create obviously PowerPoint or anything else you want. So you just click on document, then PDF, and then you can call this whatever you want. My first RMD author. And that generates it. It generates it with the title and the author that you put in. It gives it a date, and it populates it with some examples, simple examples. So if you click on this little yarn symbol icon here that says knit, you will you will be able to create a PDF based on what was preset when you create the file. And it looks something like this. Okay, and this is just what comes up when you create the RMD. Obviously, this is a nice example so that you can see what the capabilities are at a really basic level. But if you're going to do your own thing, the next thing would be to delete all of that and just start writing from there. So that's essentially how I created this one. All right, so let me tell you about the data. So I don't know how many of you have done the tutorial for Open Sesame, but this data comes basically from slight modification of that first tutorial. And the experiment is rather simple. It's a gaze queuing task. So there's going to be a letter that appears on the right side or the left side of the screen, and your task is to say what letter that is. And I think it's H versus F or something like that. In addition, the fixation point is going to be either face that kind of directs its like cartoonish eyes towards the left or towards the right, or in the case of this experiment, simply a circle that changes its proportion a little bit to indicate kind of like a ellipse type of, an ellipse type of way or egg type of way, where the target might appear. But the queuing is not perfect. Sometimes it's inconsistent. So I wanted to see if the queuing speeds you up. So that's essentially the experiment. In addition, I collected some information on my subjects, although in this data file, I only have one subject. And I'm going to tell you what that is. And that was what kind of computer they use. And subject 0 was lab 1, subject 1 was lab 2, subject 3 was MTurk. And the data for one subject is like this. My data collection, for whatever reason, gave me a lot of information. Like every trial has all of these columns: font size, whether the font was underlined, the foreground, a bunch of things that I don't even know what that they might mean. But that's what Open Sesame gave me. And maybe your data collection software gives you also a lot of stuff that you might or might not use. But we're gonna go from this mess into the type of format that we use for LMEs, for example. All right. So okay. So we're gonna learn about all of these different functions. And in our example, first we have to call our library, which, as I said, is this analogy of calling the app that allows us to use our phone. Okay, so we do that by typing the library command, library parentheses, and then the name of the libraries. So for this, in this case, I'm going to use two libraries, tidyverse and knitr. Tidyverse is what I've been referring to as these tools for data wrangling. Knitr will just create a beautiful table at the end. But if you've ever done LMEs or base factors or any of the maybe more modern statistical tools, you've used this command before, library and LME4 or whatever. Okay. All right. But after that, see how I close my chunk. And I can open a new chunk here simply by typing it. And just I'm gonna put a comment here. Oops, I missed one. There you go. You see how when I miss one, the color didn't change. So that's how I caught that there was something wrong. This chunk. Within a chunk, you can use the regular comments for R, which is the number sign or hash mark in the first character, and that just says that whatever's to the right is not going to be run. It's just a comment. But anyway, so that's how you insert a chunk. We want to start with reading the file. I put the library here again. I didn't need to, but I did anyways. So the file where my data is subject -0.csv, which is the mess that I showed you before. And to do that, we use the read_csv. Note that base R, the R that comes just from the package, has a function called read.csv. Read.csv is a more modern version. It preserves formats really well. So I prefer read_csv over read.csv. All right, so I'm gonna run this chunk. And the way that I run chunks is by pressing this kind of play button, green arrow on the top right. I can also copy and paste, but I'm not a fan of copy and pasting because then if you miss something, it's not good. All right, so I run this chunk. So this is telling me what kind of format all the different variables were read as. I'm not gonna worry too much about it, but you can see that there are like a gazillion columns that were read. Let me show you now what that looks like in my console. Oh, see how now in my data, there is a S0, which is the name that I gave to the read of that file, right? On the left side of the arrow is the name of the variable. or the data structure that I create or that I named. And it's 96 observation, meaning that probably I had 96 trials, and 121 variables, meaning that there are 121 columns, and they look like this. Open Sesame gives me, I don't know, columns that are a little wacky for somebody like myself, like the running accuracy, like up to that point in the experiment, what's the accuracy? I suppose some people might use that. The average response time up to, you know, say the 10th trial, the average response time was this up to this trial. And then there's a lot of, there are a lot of things that kind of overlap, like average RT and average response time, they're the same thing. The background, I don't know. I suppose that if you have an experiment that changes background, you might want to know that. But if it's always the same, you don't need it. And a bunch of things that I don't want to use. But you can see them all here. So obviously, you know, all of this data wrangling assumes that you know what the data is, right? And assumes that you know what you have and you know what you want at the end. But that, I guess that's obvious. Anyways, you can see that there's a lot going on here, including the experiment path. I don't know, things that I don't want to lose for sure, right? But I'm not going to use in my statistical analysis. So I need to clean things up. All right, so now I have an S0 object created. Okay, so I need to remove. I shouldn't say I need to remove. This is the right way to say it. I need to create a new object that does not include those columns that I don't want. And the reason why I say that removing is the wrong word is because it's not that I want to get rid of S0, which is what I first created. It's just that I want to use that S0 to create a new, cleaner version of the data. Okay? There are many conventions to name the product of all this data wrangling. The one that I personally use is I create an object with the same name and then a dot, and then I put in the last action that I did with it. Okay, so in this case, what I want to do is select columns. And to select columns, we use the function select. Surprise, surprise. Now, if you are an R user, or if you've ever used R for anything, even an ANOVA or a t-test or whatever, you are probably familiar with something that looks a little bit like, I don't know, like this. T.test, and oops, and then a parenthesis, and then you're gonna put X and Y, right? Where those are the two vectors that you want to do the t-test on. Or, I don't know, R norm, a classic, random normal, numbers, and you want 100 of them. So in this way of doing R, right, you have a function, and then you put the parameters of that function within the parentheses. Okay, which is it's great that works out well most of the time. And indeed, we're going to use some of that here. But when things start to become complicated, right? So for example, if you want to do a t-test of our random numbers with, and how many of them? A gazillion, with a mean of 100, standard deviation 15, for one vector, and then an exponential from, I don't know, whatever number of numbers, et cetera, you start to get a little complicated in the, you start to become a little complicated in terms of what goes in the parentheses, right? And it's easy to lose track. All right, so to solve that issue, the tidyverse tools have this operator, which is called a pipe. And essentially, it is just the percent character, the greater than character, and the percent character. So this is how it works. I'm going to use, you know what, I'm going to create a little object in my console. This is just to show you how the piping works. And that's going to be X. And X is going to be a collection of numbers, and they're going to be 1, 2, 3, 6, and 7. Oops. well, 67 and 4, whatever, it doesn't matter. All right, so that's X. If I want to, if I want to find the mean for those numbers, I can say mean of X, right? Piece of cake. But I can also use piping. And piping works like this. X, I'm going to pipe into the function mean. Okay? So now, you know, obviously the piping analogy is nice, right? Because the idea is you have an object, in this case X, and you're gonna put it through some process, and you're gonna first pipe it into the machinery that does that process. So that's exactly what we're going to do with select. So we have an object, S0, which is the big data set with all the columns that I don't want. And then we're gonna put it through the select function. The select function is simply gonna grab the columns that we tell it to grab. And in this case, just to show you one of the capabilities, I'm going to change some of the names as well. So for example, I want the title of the experiment in my clean data file. So I'm going to select that, right? So I put select, parenthesis, and then title. I want the subject number, but subject underscore NR is not a format that I'm used to. I always use subject, just subject without anything else to call my subject. So I'm going to change the name, okay? Trial N instead of count trial sequence, just because I like that name better. Type, Q, what type of Q I used, target letter, target position. Those I'm not going to change. I don't know. I'm a purist in some ways, so I like to call response time RT with uppercase T, R and uppercase T, instead of this response underscore time that my data collection software generated. So each of this is separated by a comma, okay? And each of this is a column that I'm gonna pick. All right, so I'm gonna run now this chunk. Okay, so now S0.cell, the selection, is a new object. And I haven't lost S0 as my object. And I certainly have not touched my data file. My data file is pristine and will never be opened by an Excel or by a Word or anything that could mess it up. I will always, 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 until my computer dies, have the raw data file available, okay? Never will it be touched. It will be seen, it will be read, but it will not be touched. All right, so now S0 is, S0.cell, which is a new name. The object for the name for my new object, I should say, has what you would expect: the 96 observations, but only 10 variables. Title 1, subject 2, trial and 3, so on and so forth. All right, I'm going to show it to you. There it is. Okay, I'm getting there, right? I'm getting closer to what I want, but I'm not there yet. All right, and now, you know, obviously the order of all of these operations that follows depends on what your goals are. In this case, you know, my goals were to display some of the capabilities of the tool. So I don't know if I would filter for slow responses before doing other stuff. But in this, for my example, I decided to do that. Okay, so now that I have S0.cell, I want to remove the really slow responses. And for this task, I don't know, I decided that 1.5 seconds was too slow. I don't want those responses. I don't want to analyze those responses. So the same way that we use select to pick the columns that we want, we're gonna use filter to pick the rows that we want. So select for columns, filter for rows, okay? And the rows that we want are those that have RT, which is this variable that I preserved from my big data set and that I renamed as RT. Those cases that have RTs that are less than 1500 milliseconds. All right, so I run this and I got rid of 6 files. Now, I don't know, here, I didn't think about this before, but if you want to say in your paper how many trials were removed, you can simply calculate it, right? You can say something like the dimension of S0.SEL. Let me see, I always forget what's what. Okay, so it's the number 1, so that's the number of observations. That's 96, and minus the dimension of S0.SEL dot FIL, because those are the post-filter ones. So that's going to be 6 divided by this big number, right? So those are the proportion of oh no, I did this wrong. I need to go back to second grade. Those are the proportion of trials that I lost. And I'm gonna be even fancier. I'm gonna call this lost. Okay. And now I have an object called lost. And now check this out. I lost, and then I do this. I put a comment here that calls an R object called lost. So when I do my knitting, this is going to automatically call the value of this variable. Okay, but whatever. That's kind of not. This really not. It's not tidyverse related stuff, but it shows you that you can do this automatically. You don't need to like go to your Excel and do this calculation or whatever. Okay, cool. So the next step, I think there's a question, or I saw some flashing somewhere.
Yes, there is a question that just came up. It's, can you filter more than one thing at once?
Yes. Let's suppose that you want to do this. You want to filter, and I tried this for this data set. It's just that there weren't really any really fast responses. You can say, okay, I'm going to filter for slow responses and for fast responses. So what the condition within the filter is what goes through. Okay, so my responses need to be both less than 1500 milliseconds and greater than 300 milliseconds, for example. Okay, so that would be one way to do it. You can also do it this way. You can also say, okay, I'm going to filter that, and then I'm going to pipe it again and filter for slow responses. I'm sorry, for fast responses. Why did I say 250? I think. All right, and then you know what? I'm also going to filter for. I don't have this in this case in this data set, but for example, right? I'm going to filter for practice. Let's suppose that I had a column called practice that was either true or false, and I don't want to use that in any further analysis. So I can do all of this. So those are the two ways to do it. I personally prefer to do it step by step because it's way easier to keep track of what you're doing when you do it step by step. I'm going to remove this because this doesn't exist. And I don't think this does anything.
There was also another related question, and it's, can you pipe in more than one input to a command?
No. If a command needs two things, so for example, this is a good one. What was my X? This is my X, right? And I want to do a t-test with X and then another vector, and that's going to be Y. Y is 1, 2, 3, 4, 5, 4, 7, and 9. Okay, now I want to do a t-test between X and Y. say that I can say X piped into T.test. I've never done this before. Comma Y. No, it doesn't even work that way. Yeah, I don't know. If you have a modifier of the parameter, then yes, you can pipe it, but I don't think you can pipe two things. Other questions?
I think that's it for this very moment.
Okay, great. Anyways, I'll show you this lost when we do the PDF. All right, so so far we've done three things. We have read a file, we have selected columns, and we have filtered for cases. The next thing we're going to do is create a new column. So let's suppose that you want to do the inverse of the RT. And let's suppose that your software didn't give you the accuracy. You have to calculate it by checking if the correct response is equal to the response. Okay? You do that with the function mutate. Okay? So the first, we're going to create, in this case, 3 columns. Oh, I should have put another one here. Okay, so the first one is where the target appear on the screen, and my my software, my data collection software simply put a number, and it was -300. It was probably the coordinates of the screen, -300 for left and +300 for right. So I'm going to use a simple if-else statement. If the target position is -300, then call it left, and if not, call it right. And that's going to go into a column called target side. The other new column that I'm going to create is the inverse response time, and that's equal to this formula that some people like to use. And the third one is accuracy, whether the correct response as listed in the column correct response is equal to the actual response, which is in the response column. So, I mean, this emphasizes again that you need to know what your columns are, right? There's no tidyverse that will save you from not knowing what your data you're collecting, obviously. But assuming that you know what the different columns mean, right? You can do all of this. All right, so mutate creates new columns. So remember that so cell.fill had 10 variables, 10 columns. Now our so cell fill.mute, because it's a mute after a mutate, should have what, 13 columns. Let's see. And sure enough, that happens. I'm going to open it, and you can see here all the 3 new columns, right? Great. Now, I'm pretty happy with this so far. So, but I realized that, hey, some of my subjects were through mturk, some of my subjects were in kind of like an older computer or whatever, right? So I might have a separate data set, a separate table that includes that type of information. And that's the subjects-system.csv file that I had been created, you know, maybe even manually, right? So I'm gonna read that file now here. And now I have an object called participants, which has 3 subjects, and the computer where they run the sub or whatever, how I collect it, I don't know, whatever that may be. And I'm gonna now merge the 2 tables. And the functions to merge are variations of join. And this is based on SQL language. I'm just gonna say that I'm using right join because I want to preserve all the lines on the second table in my parameters here, and they're going to be joined by subject uppercase S in the participants table and subject lowercase s in my data table. Okay, because for whatever reason, you know, I didn't do the right consistency. I wasn't consistent in naming of columns, but it's okay. I can solve that really easily. All right. So now SO join will have my 13 columns, and in addition, the computer in which the subject was run, in case I want to use that. Or if I have, I don't know, if my my demographic information was in a different table, I can use join to put it all together. So now you can see that I have something that is almost ready for analysis. I will do a couple of more things before. Oh, one thing that I don't have is whether the trial is congruent or incongruent. I know where the target size is, I know what the Q is, but I don't have a column that says congruent versus incongruent. So I'm gonna create a new column with that, with mutate, okay? After that, you probably are familiar with this issue. When you wanna run LMEs or base factors, and you read a file as characters, sometimes you run into trouble. So I wanna have factors instead of just character variables. Oh, and some people like doing this funky stuff of having negative 0.5 and positive 0.5 for their accuracy. So I'm gonna do that too, and I'm gonna create this new column called ACC.5 to where I'm gonna put that calculation. After I do all of that, I'm gonna pipe again and now select only what I want. At the end, I decided that for my analysis, I'm not gonna do the inverse RT. So at the end, I'm just gonna pick this 1, 2, 3, 4, 5, 6, 7 columns. And that's gonna be my SO final, okay? And now note here that I use the multiple piping version, but it's very easy to read, right? Here I see that I'm creating a column. Here I see that I'm creating more, and I put this separately because I figured it was so important that I want to see where I created this column. And this is more like cleaning type of stuff. And then I'm selecting what I want at the end. And I can run it. And now I have a S0 final. S0 final is here. Okay. So I don't know, almost ready. Almost ready. So the last thing that I'm going to do is I want a table that has my mean response times and my standard deviations for my congruent and my incongruent condition. But I also think that I have some bias, and I really like I was the subject for this actually. And I really like responding to the left side quickly and slowly to the right side. So I'm going to include that variable to side. And I only want my correct responses. So to create my final table, right? I grab S final, I filter because I only want the correct responses, and then this is a new function, group by. And group by means that the statistics that I'm gonna do in the next step, which is called summarize, you can also do summarize with S, either works, are gonna be grouped by these two variables, or however number of variables I want. I can actually have only one variable as well, doesn't matter. I mean, it matters for what you are gonna get, but it works with 1, 2, 3, as many variables as you want. All right, and then the summary is going to be mean and a standard deviation of RT. I'm gonna run it. Okay, and then I'm gonna put it into a cable. And you know what? This didn't run because I didn't run the library knitter before, so I need to run this chunk. And now I can run this whole thing. And it creates a nice table. Cable is a way just for this to look nice. So now that I'm happy, I'm gonna knit the whole thing. And I'm gonna have an error. Oh yeah, because I put this pipe at the end that goes nowhere. It's a bridge to nowhere. So if you put a pipe at the end, it's gonna ask you, well, where are you gonna put pipe this to? There's nothing after that. And this is my PDF with everything. So I have here the whole session, my text, every command that I run. Oh, and this is what I wanted to show you. Automatically, I call the right number here. So you can write, I mean, there's an entire library to write papers with this, and you never have to copy and paste a number. You always call the variable, and you never make a mistake that way. And the cool thing is that, okay, let's suppose that you have a new subject. Now, instead of subject 0, you have subject 0, 1, 2, and 3, and 4. You simply add the readout at the top, rerun everything, and you should have consistency. Or you forget something. You forget, oh, I should have selected a column earlier on. Then you just go back and change that, and then everything should percolate correctly. And you have this cool document that you can put in as online appendix at the end. So, obviously, nobody becomes an expert on this just by listening to some dude talk about it. So what I would really, really recommend is that you go to this book, R for Data Science, which is, I think, kind of the Bible on all of these tools. And if you're interested in kind of like a second step, would be text mining with R, which takes the same tidyverse approach, but for text mining. And both of them are available for free online. You can buy the book as well, but they are available for free online. And the very, very last thing that I want to say before the questions is that in the challenge, if you are not, if you don't want to get away from COVID-19 news, I propose this little question, right? And that is to see if the COVID cases and death rates follow the law of small numbers. And I give you a little head start, and then you can, select columns and join the two data sets, because the COVID cases and census data are in different tables. So you can join them, then sort the counties by mortality rate or by contagion rate, and so on and so forth. Cool. So that is what I have